There are many conservation laws, and I will give some more example of the laws of the same type as the conservation of charge, in the sense that it is merely a matter of counting. There is a conservation law called the conservation of baryons. A neutron can go into the photon. If we count each of these as one unit or baryon, then we do not lose the number of baryons. The neutrons carries one baryonic charge unit, or represent one baryon. A proton represents one baryon. Really, all we are doing is counting and making big words. So if the reaction I am speaking of occurs, in which the neutrons decays into the proton, an electron and anti-neutrino, the total number of the baryons does not change. However, there are other reactions in the nature. A proton plus a proton can produce a great variety of the strange object. For example, a lambda, a proton and K plus. Proton and K plus, lambda. And for example, a lambda, a proton and a K plus. So okay, a proton plus a proton can produce a great variety of the strange object. For example, a lambda, a proton and a K plus. Lambda ね。Okay. Lambda and K plus are named for peculiar particles. Okay. In this reaction, we know that we put two baryons in, but we see only one came out. So possibly either lambda or K plus has a baryon. Yes. If we study the lambda, later we discover that very slowly it disintegrates into the proton and a pi, and ultimately the pi disintegrate into the electrons and whatnot. So lambda slowly disintegrate into the pi and proton. Yes. What we have here is a baryon coming out again in the proton. So we think that lambda has a baryon number of 1, but the K plus, but the K plus does not. The K plus has 0. On our chart of the conservation laws, figure 14. Okay, then we have a charge, and now we have a similar situation with the baryons, with a special rule that our baryon number is the number of protons and plus the number of neutrons plus the number of lambdas minus the number of antiprotons minus the number of antineutrons, and so on. It is just a counting propositions. Okay, it is conserved. It comes in the unit, and nobody knows, but everybody wants to think by analogy that it is the source of the field. That is a source of the field. The reason we make these table is that we are trying to guess at the law of nuclear interaction, and this is one of the quick way to guessing at nature. If charge is the source of the field, and baryon does the same things in the other respect, it ought to be the source of the field too. Too bad that so far it does not seem to be. It is possible, but we do not know enough to be sure. There are one or two more of these counting propositions. For example, lepton numbers, and so on. But the idea is the same as with baryons. There is one, however, which is slightly different. There are in nature among these strange particles characteristic rates of the reaction, some of which are very fast and easy, and others which are very slow and hard. I do not mean easy and hard in a technical sense, in actually doing an experiment. It concerns the rate at which the reaction occurs when the particles are present. There is a clear distinction between the two kinds of reaction, which I have mentioned above: the decay of pair of protons and the much slower decay of the lambda. It turns out that if you take only the fast and easy reaction, there is one more counting law in which the lambda gets a minus 1, and the k plus gets a plus 1, and the proton gets 0. This is called the strangeness number or hyperon charge, and it appears that the rule that it is conserved is right for every easy reaction, but wrong for the slow reaction. Or on our chart, figure 14, yes. We must therefore add the conservation law called the conservation of the strangeness, or the conservation of the hyperon number, which is nearly right. This is very peculiar. We see why this quantity has been called strangeness. It is nearly true that it is conserved, and true that it comes in unit. In trying to understand the strong interactions which are involved in the nuclear force, the fact that in the strong interactions the thing is conserved has made people propose that for strong interactions it is also the source of the field. But again, we do not know. I bring these matters up to show you how conservational law can be used to guess new laws. Yes. I bring these matters up to show you how conservation laws can be used to guess new laws. Yes. The conservation law is a backbone of the science. There are other conservation laws that have been proposed from time to time of the same nature as counting. For example, chemists once thought that no matter what happened, the number of sodium atoms stayed the same. But sodium atoms are not permanent. It is possible to transmute atoms from one element to another so that the original element has completely disappeared. Yes. Another law which was for a while believed to be true was that the total mass of an object stays the same. This depends on how you define mass and whether you get mixed up with energy. The mass conservation law is contained in the next one, which I'm going to discuss. The law of conservation of energy. Of all the conservation laws that are dealing with energy, is the most difficult and abstract, and yet the most useful. It is more difficult to understand than those I have described so far, because in the case of the charge and the others, the mechanism is clear. It is more or less the conservation of the objects. This is not absolutely the case because of the problem that we get new things from old things, but it is really a matter of simply counting. Wow. The conservation of energy is a little more difficult because this time we have a number which is not charged in time, but this number does not represent any particular thing. I'd like to make a kind of a silly analogy to explain a little bit about it. I want you to imagine that the mother has a child whom she leaves alone in a room with 28 absolutely indestructible blocks. The child plays with blocks all day, and when the mother come back, she discovered that there are indeed 28 blocks. She checks all the time the conservation of blocks. This goes on for a few days, and then one day when she comes in, there are only 27 blocks. However, she finds one block lying outside the window. The child had thrown it out. The first things you must appreciate about conservation law is that you must watch the stuff you are trying to check does not go out through the wall. Yes, The same thing could happen the other way if a boy came in to play with a child, bringing some blocks with him. Obviously, these are matters you have to consider when you talk about conservation laws. Suppose one day when the mother comes to count the block, she finds that there are only 25 blocks, but suspect that the child has hidden the other 3 blocks in the little toy box. So she says, "I'm going to open the box." "No," he said. "You cannot open the box." Being a very clever mother, she would say, I know that when the box is empty, I know that when the box is empty, it weighs 16 ounces, and each block weighs 3 ounces. So what I'm going to do is to weigh the box. So totaling up the number of blocks, she would get number of blocks seen plus weight of box 16 ounce divided by 3 ounce. Whoa, such a clever mother. This is I most appreciate, right? So human. So she would get, and that add up to the 28. This to get a number of blocks seen plus weight of box 16 ounce divided by 3 ounce, and that adds up to the 28. This works all right for a while, and then one day the sum does not check up properly. However, she noticed that dirty water in the sink is changing its level. She knows that the water is 6 inches deep when there is no block in it, and that it would be rise 1/4 inch if a block was in the water. Yes. So she adds another term, and now she has a number of blocks seen plus weight of the box 16 ounce divided by 3 ounce plus height of water 6 inch divided by 1/4 inch. And once again, wow, this is so clever, mother. I appreciated that. And once again, it adds up to the 28. As the boy becomes more ingenious, and the mother continues to be equally ingenious, more and more terms must be added, all of which represent blocks, but from the mathematical standpoint are abstract calculations because the blocks are not seen. Yes. Now, I would like to draw my analogy and tell you what is common between this and the conservation of energy and what is different. First, suppose that in all of the situation you never saw any blocks. The term number of the blocks seen is never included. Then the mother would always be calculating a whole lot of terms like blocks in the box, blocks in the water, and so on. With energy, there is this difference that there are no blocks so far as we can tell. Also, unlike the case of the blocks, for energy the number that come out are not integers. I suppose it might happen to the poor mother that when she calculates one term, it comes out 6 1/8 blocks. And when she calculates another, it comes out 7/8 of the block, and the other gives 21, which still total 28. That is how it looks with energy. What we have discovered about energy is that we have a scheme with a sequence of the rules. From each different set of the rules, we can calculate a number for each different kind of the energy. When we add all the number together from all the different form of the energy, it always gives the same total. But as far as we know, there are no real units, no little ball bearings. It is abstract, purely mathematical, that there is a number such that whenever you calculate it, it does not change. I cannot interpret it any better than that. This energy has all kinds of forms analogous to the blocks in the box, blocks in the water, and so on. There is another due to the motion called kinetic energy. energy due to the gravitational interaction. Gravitational potential energy, it is called. Thermal energy, electrical energy, light energy, elastic energy in the spring, and so on. Chemical energy, nuclear energy, and there is also an energy that a particle has from its mere existence, and an energy that depends directly on its mass. The last is the contribution of Einstein. As you undoubtedly know, E equals mc square is a famous equation of the law I am talking about. Although I have mentioned a large number of energies, I would like to explain that we are not completely ignorant about this, and we do understand the relationship of the some of them to others. For instance, what we call the thermal energy is to a large extent merely the kinetic energy of the motion of the particles inside an object. Elastic energy and chemical energy both have the same origin, namely the force between the atoms. When the atoms rearrange themselves in a new pattern, some energy is changed, and if that quantity changes, it means that some other quantity also has to change. For example, if you are burning something, the chemical energy changes, and you find heat where you did not have heat before, because it all has to add up, right? Elastic energy and chemical energy are both interaction of the atoms, and we now understand these interactions to be combination of the two things, one electrical energy and the other kinetic energy. Again, only this time the formula for it is quantum mechanical. Light energy is nothing but electrical energy, because light has now been interpreted as an electric and magnetic wave. Nuclear energy is not represented in terms of the others. At the moment, I cannot say more than that it is a result of the nuclear forces. I am not just talking here about energy releases. In the uranium nucleus, there is a certain amount of energy, and when the things disintegrate, the amount of energy remaining in the nucleus changes, but the total amount of energy in the world does not change. So a lot of heat and stuff is generated in the process in order to balance up. Yes. The conservation law is very useful in many technical ways. I will give you some very simple example to show how knowing the law of conservation of energy and the formula for calculating energy, we can understand other laws. In other words, many other laws are not independent, but are simply secret ways of talking about conservation of energy. The simplest is the law of the lever. Yes. We have a lever on the pivot. The length of one arm is 1 foot and the other 4 feet. First, I must give the law for gravity energy, which is that if you have a number of weights, you take the weight of each and multiply it by its height above the ground, and this together for all the weights, and that gives the total of gravity energy. Suppose I have a 2 pounds weight on the long arm and an unknown mystic weight on the other side. X is always the unknown. So let us call it W, large W, to make it seem that we have an advance above the usual. Now the question is, how much must W be so that it just balances and swings quietly back and forth without any trouble? If it swings quietly back and forth, that means that the energy is the same whether the balance is parallel to the ground or tilted so that the 2 pound weight is, say, 1 inch above the ground. If the energy is the same, then it does not care much which way, and it does not fall over. If the 2 pound weight goes up 1 inch, how far down does W go? From the diagram, you can see that from the diagram you can see that if AO is first foot and 1 foot and OV is 4 feet, then when the V and B dash is 1 inch, AAW will be 1/4 inch. Now apply the law for the gravity energy. Before anything happened, all the heights were 0, so the total energy was 0. After the move has happened to get the gravity energy, we multiply the weight 2 pounds by the height 1 inch and add it to the unknown weight W times the height minus 1/4 inch. The sum of this mass gives the same energy as before, 0. So Z minus W over 4 equal 0. So W must be 8. Wow. This is one way we can understand the easy law, which you already knew, of course, the law of lever. But it is interesting that not only this, but hundreds of other physical laws can be closely related to various forms of energy. I showed you the example only to illustrate how useful it is. The only trouble is, of course, that in the practice, it does not really work because of the friction in a fulcrum. If I have something moving, for example, a ball rolling along at a constant height, then it will stop on account of friction. What happened to the kinetic energy of the ball? The answer is that the energy of the motion of the ball has gone into the energy of the jiggling of the atoms in the floor and in the ball. The world that we see on the large scale looks like a nice round ball when we polish it, but it is really quite complicated when looked at on a little scale. Billion of tiny atoms which all kind of irregular shapes. It is like a very rough boulder when looked at finely enough, because it is made out of these little balls. The floor is the same, a bumpy business made out of the ball. When you roll this monster boulder over the magnified floor, you can see that the little atoms are going to go snap jiggle. After the things has rolled across, the ones that are left behind are still shaking a little from the pushing and snapping that they went through. So there is left in the floor a jiggling motion or thermal energy. At first, it appears as if the law of conservation is false, but energy has a tendency to hide from us, and we need a thermometer and other instruments to make sure that it is still there. We find that energy is conserved no matter how complex the process, and even when we do not know the detailed laws. Even we do not know the detailed laws. Wow. Detailed laws, which is first law. The first demonstration of the law of the conservation of the energy was not by a physicist, but by a medical man. Yes. He demonstrated with rats. If you burn food, you can find out how much heat is generated. If you then feed the same amount of food to rats, it is converted with oxygen into the carbon dioxide in the same way as in burning. When you measure the energy in each case, you find out the living creatures do exactly the same as non-living creatures. The law for conservation of energy is as true for life as for other phenomena. Incidentally, it is interesting that every law or principles that we know for dead things and that we can test on the great phenomenon of life works just as well there. There is no evidence yet that what goes on in a living creature is necessarily different so far as the physical law are concerned from what going on in the non-living things, although the living things may be much more complicated. the amount of energy in the food which will tell you how much heat, mechanical work, etc. it can generate is measured in calories. When you hear of calories, you are not eating something called calories. That is simply the measure of the amount of the heat energy that is in the food. Physicists sometimes feel so superior and smart that other people would like to catch them out once on something. I will give you something to get them on, okay? They should be utterly ashamed of the way they take energy and measure it in a host of different ways, with different names. It is absurd that energy can be measured in calories, in ergs, in electron volts, in foot-pounds, in BTUs, in horsepower hours, in kilowatt hours, all measuring exactly the same thing. It is like having money in dollars, pounds, and so on. But unlike the economic situation where the ratio can change, these dopey things are in absolutely guaranteed proportion. If anything is analogous, if anything is analogous, it is like shillings and pounds. There are always 20 shillings to the pound. But one complication that the physicists allow is that instead of having a number like 20, he has an irrational ratio like 1.6183178 shillings to a pound. You would think that at least more modern high-class theoretical physicists would use a common unit, but you find papers you find a paper with degree Kelvin for measuring energy, megacycles, and now inverse Fermis. The latest invention. For those who want some proof that physicists are human, the proof is in the idiocy of all the different units which they use for measuring energy. Haha.